Alright, we're going to look at numerical approximations of solutions to differential equations. And so for this, we're going to look at first order differential equations. There are some methods that can be extended to higher order differential equations or systems of differential equations, but we'll just really be focusing on first order differential equations for this class. So the idea is that we're going to have a first order differential equation. For the formulas we're going to use, we're going to want that solved for dy dx, and then we'll also need an initial condition. And the idea here is that we want a good graph of that solution curve so we can make some predictions about what that solution curve is going to do without necessarily finding an explicit solution. So we'll look at an example and talk in that example about why that would be a helpful thing to do for that particular example. And then the key idea is really one from Calculus 1, and that is that tangent lines are good approximations for curves. And I just want to say a couple of caveats about that. I would say usually, occasionally you run into some trouble with a curve that's behaving kind of irregularly, and in that case tangent lines might not be great approximations for curves. And then the other thing that I want to emphasize about that is that they are approximations, and so there is a source of error, and so we'll talk about that a little bit too as we look at these. Okay, so the basic idea is that we're going to use the equation of a line to predict new points. So if we've got an initial condition, y of x naught equals y naught, that's an initial point. Often that point might be given at x naught equals 0, but not always. I'm going to draw my point here with the x naught being 0. But we've got a point, and then we've got a differential equation, dy dx equals f of xy, and the key is that dy dx represents a slope. And so if I put that point, x naught, y naught, into my differential equation, I'm going to get a slope that is the right-hand side of the differential equation evaluated at that point, x naught, y naught. And so that'll give me a slope of a tangent line through that point. So I'm just going to draw a little tangent line through that point with some particular slope. All right, so if what we're looking at is a differential equation whose solution is a curve, then it doesn't exactly match that tangent line, but at least locally, at least on a small little interval, we can use that tangent line as a good approximation for the curve. And then the idea is that you would use that little tangent line to identify another point, some specific distance away. I'll call that x1, y1. So I'm just going to use that equation of the line to get a new point, a little bit of a distance away. And then I'm going to repeat the process. So I'm going to plug that point, that new x1, y1, into the right-hand side of my differential equation, and I'll get some other slope. I'm going to assume this time that it's a little bit bigger number, so I'll have a little bit steeper slope here. Right? And then you just keep repeating the process. So after you follow that little line segment for a little bit, you identify a new point, say x2, y2. You plug that point into the right-hand side of the differential equation to get a new slope, and you can basically build an approximation for the curve using these little tangent lines. All right, so there are some formulas associated with this. And so we're not going to do a bunch of number crunching with the formulas, but the key thing that I want you to recognize is that these formulas are really about equations of lines. And so over here to the right, I've written down the basic form of an equation of a line from algebra. This is point slope form of a line. So y minus y naught, whatever your starting point is, equals m times x minus x naught. And then the key thing here is that our m is given by that f of x naught, y naught. And so I use that equation of the line to get my next point. And so then the question is, how do you get that next point? And so basically there's some decision that you're going to make on a value for delta x. So you're going to choose that ahead of time. And some of the more sophisticated numerical approximation methods actually choose that delta x based on what the slopes are like, so that when there are really steep slopes, they're choosing very small delta x's, and when the slopes aren't as steep, they'll choose larger delta x's. So the delta x will tell you how far your x coordinates are between your points, and so generally for what we will be using, we're going to have that same width there between all the points. So you're going to choose that, and then you're going to use that to get your next x-coordinate and all your subsequent x-coordinates. So your next x-coordinate, your x1, is going to be your x0 plus your delta x. And then you want to find your next y-coordinate. So your y-coordinate is going to be a solution to that equation of the line. I'm going to add the y0 term to the right-hand side here. So the m would be the f of x0, y0. And then the x minus x0, so at your new x-coordinate point, that's going to be your x1 minus x0, or delta x. Notice that what's here in this parentheses here is the difference between two x-coordinates. So essentially you just keep reiterating this process over and over and over again. So your y2 then would be f of x1, y1 times delta x and plus the prior y coordinate. So each time you're just reusing that prior xy coordinate to get a new slope and to get a new y coordinate. And your new x coordinates will just be based on your prior x value plus delta x. Okay, so we're going to go down here and look at a table and kind of do a little bit of calculations. I'm also going to use an app to do kind of the heavy lifting on most of the calculations, but we'll do a couple just by hand to make sure that we're clear about what exactly is happening. Alright, so here we have an example, and I want to talk a little bit about this differential equation before we dig into actually using Euler's method here. So this differential equation, you should notice that it's first order, it is nonlinear, it is not a separable differential equation, and it is also none of the other kinds of differential equations that we studied methods for solving. So it is not a Bernoulli equation, it's not a homogeneous equation, it's not one that we can solve using a substitution. So none of the other methods that we studied apply here. So essentially I'm going to look at numerical methods to help me solve this. So I might look at a slope field, and then I could use that slope field to help me find some solution curves. And essentially that's what we're doing here. If you remember looking at those slope fields, it was a bunch of little tangent lines, which is what I was drawing up above. The other thing that's relevant here though is I could think about using the appropriate existence and uniqueness theorem for this differential equation. The existence and uniqueness theorem that I would use here would be the one that we called theorem 1. That one was for generic first order differential equations. And if you think about the right hand side, the f of xy function, and also the partial derivative of f with respect to y, those are both continuous everywhere on all of our 2. And so that theorem tells us that a unique solution exists, at least on some neighborhood around the point that we're given. So I'm just going to put here near x equals 0. Okay, so I've made a chart here because we're going to do some of this by hand. And then there's something else here. It has used h. So in the numerical methods in our text, and this is pretty common in a lot of textbooks, they will use h for the delta x value that you're going to be doing here. Alright, so in my chart here, I'm going to label a couple of different things here, and you could do this in whatever way you want, but I want to kind of emphasize some specific things here. So I'm going to label an x-coordinate and a y-coordinate in the second and third column, and then in my first column I'm going to use k, and the k is going to indicate the iteration, so I end up with a sequence of points here. So we'll start with k equals 0, so our first point will be our x0, which was given, and the y0, which was also given. That's our initial condition. And then I'm going to also over here calculate the slope at that point, which will be given by the right hand side of the differential equation with that particular point plugged in. And I'm going to write out a little bit for these first few calculations, but then we'll look at using an app to kind of finish off the calculations here. Alright, so I have set this table up here, so we're going to do 4 iterations. And so if my delta x is 0.5, then our points are going to just increase for the x's by 0.5. And so in this case, the last point that I'm going to approximate is x equals 2. All right, so for the calculations here, this first one, I'm going to calculate the first slope by plugging my point 0, 1 into that right-hand side of the differential equation. So we end up getting about 1.84147. All right, and then the idea is that I'm just going to use that prior x and y coordinate to get my new y coordinate. So I'm going to write down what the actual calculation is going to be here. So I'm basically using my y equals m, so that's that prior slope. I'm just going to write the approximation here. I'll just write a couple decimal places of accuracy. The prior slope times the delta x. The delta x is always going to be 0.5 plus the prior y coordinate. All right, so that's from the basis of that formula that we had there. All right, and so I'm going to write down a few more decimal places of accuracy than I have written here. So I kept lots of decimal places of accuracy in my computer when I did these calculations. So I got 1.92074. Okay, and then in order to do the next iteration, I'll need a new slope, and I'll use that to get a new point where I have the x coordinate of 1, and I'll get the y coordinate. And so you want to be careful about this. One of the things that we'll talk about down here is what are some of the possible sources of error and how might you minimize those sources of error. So I'm exhibiting 1 right now. I've written down some approximations just rounded to a couple of decimal places. Generally, you would want a computer to do these calculations, and it would store lots more decimal places than you might care to write down. But I'm just writing down a few here. All right, so that first slope, or the m1, the slope at the point 0.5 comma approximately 1.92, for that slope I get approximately 1.89976. Okay, and then I'm going to keep just repeating that process. I'm going to write down one more calculation here. So we're going to use the slope, the prior slope, so approximately 1.90 times the delta x plus the prior y coordinate, approximately 1.92, and that's approximated. And with more decimal places of accuracy here, I get 2.87062. Okay, so we're just going to keep reiterating that process. I'm going to go ahead and fill in these values here for what I got for the next couple slopes and points. Okay, so I've written down several of those values here for slopes and points. I did not calculate the slope at the last point because I didn't really need it. Remember that those slopes are really being used to predict the next point. So if I'm only going here to x equals 2, then I don't really need another slope that would be used to predict a point at x equals 2.5. All right, I'm going to pull up an app, and I want to show you a little bit how I would use that app to actually get some of these values. So there is a link in Canvas for this app, or here is the URL for the app that I'm going to be using. Okay, so I've pulled up the app here, and there's some information at the top here that is helpful to read just so you're clear about what you're looking at. So we are able to enter information about a differential equation of the form dy of dt equals f of ty. So independent variable t, dependent variable y, and in our example we were using x for the independent variable. On an interval from t sub 0 to t sub 1. So t0 would be your starting input value, t1 would be your ending. So for our table, we went from 0 to 2, and then an initial condition y of t naught equals y naught. And it tells you that it uses several different methods, so those other methods are other ones we're going to be looking at. And then it has some instructions there about how to enter functions. So for example, you'll use expt to enter e to the t, and hyperbolic sign is there. And then some other instructions here about star for multiplication, a slash for divide, and a caret or double star for powers. And just some reminders here that you need to put some parentheses around the arguments of your functions. All right, so I've got Euler tangent line method chosen here. I'm going to leave that chosen, and then I'm going to enter here the right-hand side of our differential equation using t and y instead of x and y. All right, so I've got my right-hand side of the differential equation entered here. I want to start at t naught equals 0, and our initial value was y naught equals 1. Our t1, so the ending t value in our table was 2, and our step size was 0.5. Okay, and then the other thing that I'm going to choose here is the output format. So the default is graph only, but we want some numerical values. So it's gone off the bottom of the screen here, but when you expand that, one of the choices is graph and data points. So that's what I've chosen here. And then I'm going to click submit. All right, and so we've got up here at the top the information we entered. There is a graph of the solution, so like I was drawing with some little line segments connected with each other, approximating a curve. And then down here at the bottom, solution data points. So it's not labeled, so you just want to be clear about what these values are. The first column here is the t values starting at 0 and ending at 2. And then the second column is the y values that we had in our table here, given to 6 decimal places. If you wanted more digits of accuracy, then you could perhaps use a different app or a spreadsheet. But for this app, these are good enough for what we're going to be looking at here. All right, so we'll use that, and then we'll use some of the other features on here as well to examine other numerical methods. You can use lots of different apps. There are lots available on the web, but I really like this one because it does all the 3 that we study, and I like that it outputs both a graph and the data points that we've got from our numerical method. Okay, so let's go back to the notes here and talk about these things here at the bottom and what are some possible sources of error. So the first one is one I actually already talked about and was really evident in what we just looked at. It uses line segments, and line segments are not the same as curves. Another issue is that when you choose a delta x that's pretty large, a delta x or h value that's pretty large, you're choosing points that are fairly far away from each other. And if you've used a line segment to approximate and the curve really went in a different direction, you're going to end up off by quite a bit where you end up with that second point. So in general, a large delta x or h value results in less accuracy. And that sort of also answers that next question. Another source of error here, and I talked about this a little bit when I was writing stuff down in the table, but at every step where you've got a decimal approximation, you've lost some information depending on how many decimal places you chose to keep. So another possible source of error is round-off error at each step. One other issue too, in addition to round-off error at each step, because you're using those answers in one step to generate values in another step, you end up with what's called propagated round-off error. So you're using a imprecise value at one step and then using that to get another imprecise value. So you end up with what's called propagated round-off error. So that's basically using those imprecise answers to calculate more answers there. Another thing to think about is that if you have something where your solution to the differential equation actually would end, so perhaps it would come up against an endpoint of domain or a place where it fails to be differentiable beyond that, maybe an asymptote. These numerical methods sometimes can skip over that. So if your actual solution curve went something like this and had an asymptote, and then you use numerical methods, you might do line segment and get a slope and get another point here, and then perhaps that curve has a different line segment, that curve that would go through that second point, and so it'll get maybe another point over here, and it will just skip right over that asymptote. And so if the actual curve that you're trying to find has any sort of erratic behavior, then you have to be aware that your numerical method might not pick that up. There is an example at the end of section 2.4 that illustrates some things with that. In general, if you want to make sure that you're getting good results, you really should use a variety of methods. So we'll talk about a couple more methods here. and a variety of step sizes. And what you're looking for there is stability in your answers. So again, what you're looking for there is consistency, so that when you do several different methods and several different h values, you're getting similar-ish results. The other thing I want to stress here too is that in this example, I did a step size of 0.5. Generally, that's way bigger than you would do in any kind of numerical method. That's pretty big. Generally, you would use a much smaller h value. I did that intentionally so that we could see those line segments and do some calculations by hand here. But generally, you would probably, even if you're going just 0 to 2, use a much smaller step size like 0.1 or something like that. So, all right, watch the other videos and try some problems.